Go.
All right, good morning, everybody. My name is Virginia Hernandez.
And Ruben Diaz.
And for today's design review, we would like to present to you our 64-bit processor, Caesar. Today we're going to be going over our logo introduction first. Then we're going to talk about our baseline, and then our processor design, the enhancements that we implemented, and future plans that we would like to share with you guys. And we'll be finishing with the closing and Q&A session. So we first knew that we wanted to create an encryption processor. So we started researching, and we found out that Julius Caesar was actually, he had a cipher, and it was one of the first recorded that he used for military messages. So then we started developing our company name, and we came up with Ulterion, which derives from the word ulterior, meaning existing beyond what's obvious or admitted, intentionally hidden. So our baseline consists of a Harvard memory architecture, a 32-bit address space, 64-bit memory operands in the Little Indian format, 32 integer registers, and 32 floating point registers, both 64-bit byte, 5-bit flag registers, which is a carry, overflow, negative, 0, and interrupt enable. We're going to have 3 addressing modes, which are your immediate, register, and register indirect. These are totaling 80 instructions that were covered in the baseline. And I'm going to talk about the instruction format right now. So for our triple operand instruction format, we use an 8-bit opcode, which is implemented throughout all instructions. We have our source 1 register, our source 2 register field, and our destination register, which all all 5-bit operands. Our double operand instruction format, we only use our source 1 register and our destination register. For our single operand instruction, we only use the same as destination and source 1 register field. For our conditional jump instruction, we use the opcode and a 24-bit signed displacement field. For our unconditional jumps, calls, and return instruction, we use only source 1 and the opcode. And for our flags and processor instruction format, we're going to just use our opcode. Immediate operand instructions, we use the destination source 1 and an 8-bit immediate value, as well as our destination register. For our floating point instruction, we use both source 1 and source 2, and as well as our destination register.
All right, I'll be going over the processor design. We start with a top-level diagram. We have our Caesar processor with the 3 memory modules. We have the I/O memory, the data memory, and the instruction memory. Now inside the processor, we have the control unit and the execution unit. Here in the middle, we have the control signals going from the control unit to the execution unit. And we only have a few signals going from the execution unit back to the control unit. And those are the flags for the integer, also the floating point flags, and we have the flags from the encryption unit, and the flags coming back from when you return from an interrupt. Now we're inside the execution unit. On this diagram, we only have control signals because there's so many that we couldn't fit the data path. We have the floating point unit, the integer data path, the encryption unit, and the bus interface. Now this is the data path for all modules. We have the floating point data path, which connects to the BIU. We have the integer data path, which connects to the BIU and also communicates with the encryption unit. We have the encryption unit that only communicates with an integer data path. And we have the bus interface that communicates with the memory outside and all the modules inside, except the encryption unit.
Hey, go back, Ruben, for a sec. What's that one little rectangular box there?
Right here?
Yeah.
That's actually a SAN extension.
Okay.
Yeah. It brings in the bits from IR and extends them. So this is the floating point data path. We didn't change anything from the one that we had at the beginning. The only thing that we added was inside the ALU, which is opcode 14, which it helps us do the logical OR. when we bring the floating point or high. Now this is our BIU. We have our, so we have the floating point write buffers here. We have the read buffers. We have the memory address register, stack pointer. We have the write buffers. Also we have the IP and IR registers. Now on this BIU, one of the important things that we had to implement was how are we going to save the flag when we go into interrupt. The way that we do it is when we hit an interrupt, we save the current address from the IP into write buff 0. And at the same time, we save the current status of the flags into write buff 1. Then we take the steps of saving the memory and flags into them into memory.
And those muxes up at the top, some of those had to be added or changed?
Yeah, correct. This mux right here has to be added. When we hit the interrupt, it has to go to 3FF. So here we have to load that value, 3FF. We also had to, when we need to do jumps, we had to add that the address that is on the lower 24 bits of the instruction. We have to add them here with the current IP, and we have to load the IP.
Mm-hmm.
Also, when we come back from an interrupt or any call, the address comes back to the read buff 0, and it has to go back into IP. Now here, the write buff 0 has also a mux, which is it has to choose between integer data path information and also the current IP. And here's the mux for write buff 1, which is still, it chooses between the integer data path information or the current status of the registers.
Mm-hmm.
The current status of the flags. All right. Now, we implemented inside the BIU our regular register. We had a general format, which it has the load, reset, clock, also an increment signal. The only thing that we had to change was for a stack pointer, because when you reset stack pointer, you have to go to 3FF instead of going to 0. So we made our own register for that. Also, when we do a call, we save the current address of the current value of the IP into write buff 0. And we wanted to make sure that write buff 1 had zeros. So in here, for our reset, we did a reset or a 0 write buff. 0 write buff is a signal from the control unit that just makes sure that that register becomes 0.
Mm-hmm.
So we implemented a couple enhancements, 3 actually. We implemented a barrel shifter, 8, 16, and 32-bit operand instructions, and an AES cryptography unit. So the barrel shifter, first thing, is a digital circuit that can shift data by specific number of bits in one clock cycle.
Okay, the way that we implemented this barrel shifter, we added the barrel shifter in parallel with the ALU's box. We'll talk about that one later on.
Mm-hmm.
We have a mux that selects the data coming in from the outside integer data path. But at all times this guy is working. The only thing that you will actually select the data coming out of the mux. Okay, the instructions for the barrel shifter are barrel shifter, barrel rotate right, barrel rotate left, barrel logical shift left, barrel logical shift right, and barrel arithmetic shift right. Now this is the instruction format that we have. We still have the 8-bit opcode. We have the 5-bit source 1 field. Instead of having a source 2 field, we have to change it into a shift and rotate amount, which is 6 bits. And we have our destination register field, which is 5 bits.
Mm-hmm.
So an example we want to share with you guys today is the barrel rotate left, which in this case, it says that we want to rotate 3 bits from register 3 and store them into register 2. So it will animate the bits rotating. So the upper 3 bits will rotate down to the lower 3, and then the upper 5 will push up.
Now this is the implementation of our barrel shifter and the Verilog code. Now we didn't want to go with the big case statements. So now we have the 5 modes here. The first mode, we have your typical shift operator with a shift amount. For mode 2, which is the logical shift left, we have the logical operator with a shift and out. Now for rotates, the way that we had to implement it was we had to actually duplicate the data coming in to make 128 bits. And now when we do the rotate, we just give it the shift amount, and as the one at the bottom is shifting to the right, the upper 64 are coming in into the upper bits of the lower 64. Same concept for the rotate left. Now the key right here is that rotate left is the same thing as rotate right, but you just do it 64 minus the amount, just right here, and we do the same implementation. Now for the arithmetic shift right, it was a little more complicated. So we had to do, we shift the data coming in for the shift amount. We shift it to the right and right again to the left, so we can actually save the bit. Now, we have to OR it back with a 64, we have to replicate 64 times the last bit.
Oh, yeah.
And then we shift it to the right, 64 minus shift amount, which is almost the same thing as rotate left. And now because we couldn't do it on the same line, because silence was, Verilog doesn't let us do it, we had to create another line, and here now we have this helper value, which is the one that we have generated, and we do the same thing as we did in rotate right. We duplicate it, and we do the shift amount to the right.
You have an example of that with numbers?
No, I don't.
Oh, too bad.
On the ISA we do, but not in here too,
Yeah, yeah.
for the time.
So our second enhancement is our 8, 16, and 32-bit operand instructions. This gives the user a larger space in the register file, having the ability to utilize more pieces of a 64-bit register.
So we currently have 32 registers, 64 bits wide. But now from those, we can actually make 64, 32 bits wide. No, 64, 32 bits wide. Then also we can make 120 registers, 16 bits wide. We can also make 256 registers, 8 bits wide. The format is as follows. For the 8-bit operands, we have your 8-bit opcode, source 1, source 2, which are all 8 bits, and also destination register. Now, this right here, the lower 3 bits are the index of the actual register. So you have 3 bits, which is 8 different indexes. And we have the register that you want to actually address. You have 0 to 31. The same goes for source 2 and source 1.
But as far as the assembly language, it could be 0 to 255.
Yeah.
And that's how you break it up. Yeah.
The same concept follows for 60-bit operands, 16-bit operands. The only thing that we don't use one of the bits. Also for our 32-bit operands. Now, the things that we had to add to the integer data path to achieve this enhancement was data insertion module, which goes on top of the integer register file that we have. We had to put an extra data output on the register file. And we had to create the ALU box, which contains 4 ALUs, the 8-bit, 16-bit, and 32. All right. Now, the data insertion module, the way that it works is that it receives 64 bits, but depending on the mode, it's how many bits it grabs from bit 0 all the way to 64. So, for example, for the 8-bit mode, 88 will have to be on bits 0 to 7 from the data coming in. And by using the index and the mode, it will actually insert the value and the correct location of the current value on that register. So this is the Verilog module that we created. Now value in is the new value that you want to save into the register. Current input is going back here, it's this input coming in from the register file. And that one brings in the current value that the register has at that moment. And then you have your index, which is 3 bits. You have from 0 to 7. And that's the 8-bit mode, but you can actually go from 0 to 3 for the 16-bit and 0 to 1 for the 32-bit. Now you have a case statement here. The first portion here is for the 8-bit mode. It actually inserts the value in the correct location, depending on the index that you want. Here is the 16-bit mode, same concept as the 8-bit mode. And here's the 32-bit mode. Now, if you don't want to use a 32-bit, 16, or 8, it'll be a 64, which the value coming in will be the value coming out. Now, inside the ALU box, we have the 4 ALUs. Now, in order for us to feed the correct byte, or 16 bits of 32, we had to create this modules called hats. For the 8-bit hat, we actually, for the 8-bit hat, you receive a 64-bit input, but according to the index that you give it, is the index that's going to select. In this case, if we give it an index of 2, it will grab 88, and it will output 88 through S, and the same concept goes with R. Okay? Now, all the ALUs are working at the same time, so depending on the mode that you're using, 8, 16, 32, or 64, it's actually the flags that are going to be outputted, and also the data is going to be outputting here. So this is the code for the ALU 8 hat. You receive the index of the R side and the index of the S side. You receive the R input and the S input, which is 64 bits, and your output will be 8 bits. Right? It's a case statement for the S side and the R side, depending on the index that you give it. Same concept goes for the 16-bit, but lower cases, and then 32-bit. On the 32-bit, we didn't have to do a case statement, we just used an assign statement. All right. Now, with this enhancement, we have the ability to have 66 new instructions. Now, for this thing, we just added the X. You can just put 8, 16, or 32. We have add, subtract, multiply, all the ones that we have implemented for the 64 bits.
Now we get to our last enhancement.
Last but not least.
Not least. Cryptography, right? So that's the practice and the study of techniques for secure communication in the presence of third party. So we define encryption, right? What is encryption? Encryption is the process of encoding messages or information in such a way that only authorized parties can read it. So if we were to encrypt it, this is using the Caesar cipher rotated by 3.
Okay, so what's decryption? Decryption is the process of decoding data that has been encrypted into a secret format. What we did right there, we decrypted the text that was there using Caesar cipher rotate 3. So
we use the AES, which is the Advanced Encryption Standard specification, which is used now actually by the NIST. It was founded in 2001.
The key feature for this encryption is that you have 10 cycles or repetitions for 128-bit keys. We also have symmetric method, which means that you have the same key for encryption and decryption.
So for the encryption process, we're going to be generating a 4x4 column major order matrix of bytes. We call this one the state table. So for example, we're going to be encrypting CECS 14. So what we do is we convert those ASCII into ASCII 128-bit, and then starting with the most significant byte, we're going to place each value in the table. So that's all. So it's placing them in column, that's why it's column major.
Column major form.
And we do the same thing for a cipher key table, which is going to be the 128-bit value that's going to be encrypting or decrypting.
And where does the key come from?
It's a value that you can generate yourself. It's not a specific mathematical thing behind it.
Not a random number generator type?
It could be random number generator. It doesn't have any real meaning. It has to be just 128 bits.
Yeah. But in your machine, where did it come from?
We actually use a website. So when we're developing the actual encryption, we have to go to a website where they give us test vectors. So we know what the actual values coming out they're supposed to be. And this is coming out from that website.
Okay. So your machine will always use that key?
No. Actually, we have instructions that will set the key depending on the
Okay,
user.
okay,
Yeah.
okay.
That's for the example.
That's what I meant.
Yeah.
Good, okay, great.
So for the previous process, the way that we implemented on Verilog, we actually have two 32 by 4 registers. One of them is going to keep track of the key, which is the PS scheduler, and the other one is going to keep track of the current state of the data that you're going to encrypt. And here we actually, it's just assigning bytes to each location of the 32 by 4 registers.
So the first state in this encryption process is called the add round key. And here we're going to take each row from the current state and XOR it with the cipher key table that we had made before. So
Okay.
this is going to create the new current state table.
On Verilog, the way that we implement it is just, we have your input state. We're going to XOR each of the rows with the current key and just assign it back to the input state.
So that's step one.
Correct. Yes.
We set our counter to 0 because we're going to be going through this loop 9 times. Then we do our first process, which is called subbytes. So here we're going to be using a lookup table called SBox, and it's basically going to be mapping out the current state with the Xbox values.
Okay. The way to implement this is we did a nested for loop. It goes through column by column, and in each column we go row, and each element in the row. Now we have a lookup table for the SBox with 256 values. The way that we do it, we grab the first byte, we assign it, there you go, we assign it to the SBox input. We have to wait 1 time unit in order to get the answer back. Then once we get the answer back, we actually assign it to the new location. We do that through all the elements on the table, and we get a new current state.
So you get a #1 there, right?
Yeah.
Can this synthesize? This
No.
code?
No.
How would you get it to synthesize? Another day, another day.
So then we go into our shift row state, which here we're going to be taking the first row, and we're not going to be modifying it. Our second row, we're going to be rotating the entire row once left.
Mm-hmm.
And then the third row, we're going to rotate left twice. And then we're going to rotate left on the last row.
3 times.
Yes.
Now in Verilog, we did a simple, just we go through, on the first row we don't do anything. On the second one, we actually have to grab the first byte and put it at the beginning of the row. On the third one, we actually have to grab the 2 most significant bytes and put them at the beginning. And on the last one, we have to grab the 3 most significant bytes and put them at the beginning.
Then we mix the columns. So here we're going to take our next state table, and we're going to take our first column. We're going to be multiplying it by our mixed column matrix, which is a lookup table. Every number in the matrix corresponds to a multiply by, and then the number in the matrix. So we take our first element, which is D4, and we're going to be going to the multiply by 2 column. So the first nibble is D, which determines the row. Then we go to 4, which is our columns. When we go to D4, we're going to find the value B3. So that's the first value that we're going to be XORing. And you just continue the process to get the 4 values, and you get your result, which is 4. So that's demonstrating the second value. So you go to your multiply by 3 table here. Then to get the third and fourth value, since it's 1, multiplying by 1 doesn't change it. So that's what you get.
Now for Verilog, we could have done the lookup table, but we actually went with mathematics. So instead of using the lookup table for multiply by 2, what we can do is when you have the original value, you shift to the left once, and if the most significant bit is a 1, you have to XOR it as 1B. Okay?
Why
So here's
1B? Why 1B?
Now, the reason why 1B is there's a mathematical thing behind it. I didn't have enough time to look into
Okay.
it. I just know that if the most significant bit is a 1, you have to
Okay.
do the XOR with 1B. So here we do the check. If the most significant bit is a 1, you XOR with 1B, otherwise with 0. And you XOR with a value in that location. Now here is the multiply by 3 table, which is you shift to the left by 1's the value, you XOR with itself, and if the same thing, if the most significant bit is a 1, you XOR with 1B, otherwise with 0. Here is the check for the most significant bit, then you XOR with itself, and then you XOR with a shift left. Now because multiplying it by 1 doesn't get any change, we just put the values in there.
Mm-hmm.
And the same thing goes down the rows and down the matrix.
So the organization, go back one slide, Ruben. The multiply matrix, is that for the AES algorithm, like the 2, 3, 1, 1 and the 1, 2, 3, 1?
Yes, it's specific.
So it's not random?
No, that
Okay.
one is specific.
So then we go into our schedule round key state. Here there's 3 processes that are involved. The first one is called the rot word, where we take the last column and we take the first value and then we push it down, and all the rest of the values we push up. Then we put that back into the cipher key table.
Now in Verilog, there you go. Verilog, we just implemented, we created an 8 by 4 register, and now we assign each of those values to that register. We just put down the 1, 0 location, and we put 3, 2, 1.
Our second process within the generating the round key is called subbytes. Same as before, where we take the first nibble, and that determines the row, and then the nibble is the column. So here for CF, you go to row C, column F, you get 8A.
Mm-hmm.
You put that into the next column that you're going to be generating.
Now going back to the same process that we did before, we have a lookup table for the S box in. We have the one-time unit to wait for the answer, and with the same process down the column.
So that value that you created, you're going to be XORing with the first row of that cipher key. So you're going to take the first column, and you're going to XOR it with
What
the
you pulled
sub
out.
key.
Mm-hmm.
And then we use an RCON table, another lookup table, so we're going to XOR it with that first column.
Now all these lookup tables that we've been using, they're specific to the AES.
Okay, yeah.
encryption.
So then you generate your new column.
Now in the Verilog code, we have the PS scheduler, which is the current state of the key that we're working with. And we're gonna do the subbytes. This is actually the column that we generated before in the previous step. Now we have this new column, which is the current one all the way on the left. Right here is 3124. And we're gonna do the first one as the only one that gets actually XOR with the RCON value, because the rest of them have zeros.
So now the RCON results are going to go into this new round key table that we're going to generate. And the process is a little different now. You're going to be getting the second column from the cipher key table and XORing that with the first column of the round key values. So that will go into the second column. And then to generate the third column, you take the cipher key third column and XOR that with the second column of the round key table. Then that determines your third column for the round key. And then you're going to use a new column and we XOR it with the next column for the current key to create the last one.
Now on this step right here, we just changed the key that we're encrypting with. So we did an encryption within the encryption key. So now we changed the key to get a new round. Now all the steps right here, they're on 3 different locations. This is the same state on the state diagram. We have the first step you talked about here. Then we have here the second one and the last one, which actually all in together create the whole state table. of the new key.
So our last state within the loop is called an add round key, which you XOR that data with the round key table. So here, you're going to be doing the current state, XORing it with the round key, and then you get your current state.
And you have the same Verilog code that we did the previous one in the first step. We do the current state with the current key, and we just XOR and take the place of the input state.
So then you check if you've looped 9 times already. If you have, you exit the loop, and then you go into your subbytes one more time. You shift rows, and you add the round key for the last time.
My goodness.
Okay, this is the cryptography unit block diagram. We have an encryption part and decryption. Now, we're not going to go into a decryption explanation because it's going to take too long.
Mm-hmm.
But pretty much the way that you decrypt it is you have to go all the steps in reverse.
Mm-hmm.
But the matrix that we're going to use is different. Now you're using multiply by 14, multiply by 13, and multiply by 11.
Mm.
And now, on those, the mathematics didn't work out as well as for the multiply by 2. So actually we had to create, lookup tables for all of them. But we didn't write them ourselves, we just created a Java program that did it for us.
Mm.
So that's how we did it. So in here, this is actually the key for encryption and the data for encryption. There's instructions in our processor that load those values in here. Also for the decryption, the same thing, have the key and the data to decrypt. Once you're ready to encrypt, you have to give it a signal to actually start encrypting right here. It comes in from the control unit. For encryption, it's going to take 51 clock cycles, and for decryption, it's going to take 45. The difference between the clock cycles is because on decryption, we generate all the round keys at once, rather than just going adding an extra state into our state machine. Once the encryption or decryption is done, the unit is going to signal the control unit that they're done. So right here, the done encryption and done decryption. But the control unit doesn't actually check those bits all the time. So you have to tell the control unit to check it. And that's called the Caesar update instruction. Now, when you get the values, they're right here, the answer. And you cannot start a new encryption until you actually get those values and you put them into enter data path. And you have right here a mug that selects each of those 64-bit registers, because your answer will be 128. So you have to select which of the 64 goes first. Now the new instructions that we have are the set encryption key, which is going to load the values into the encryption key field. Set encryption data, which is going to load the data that you want to encrypt into the unit.
Now, how much data is that?
128 bits.
Okay.
Okay. Then we have the encrypt signal, which is, sets the machine to start encrypting. You have the encrypted data, get encrypted data, which gets the results from the encryption. You have the jump encryption done, which is a jump instruction.
Still waiting, right?
Yeah. Now, the way that it works, you can be waiting, just looping, or you can actually go out and start doing your other work and later on actually check if they're done. So the machine keeps going. It's not in a whole location.
You didn't generate an interrupt. That would have been
No,
nice, right?
that would be an enhancement.
Yeah.
Same thing for that decryption. We have the same type of instructions. And here is the Caesar update, which it goes and it checks those flags that done decode and done decryption and done encryption. This is our new format. We have the 8-bit opcode, and now because all the time we're loading 120 bits and we're getting 128 bits, we use the source 1 register as the lower 64 bits and the source 2 register as the high 64 bits. So if you want to load the key, you will put the 64 bits right here, the lower ones, and then the high ones.
Okay.
Some future plans that we would like to share with you.
Okay. So we would like to add the MMX unit, multimedia extension. We actually had it, but because of time, we had to remove it. We would like to implement a pipeline 7-stage pipeline with forwarding. Now we would like to go to a superscalar thing, which is to having 2 clocks per instruction. And also we would like to implement other algorithms into the encryption unit. We were looking into the RSA encryption, which is not symmetric, it's asymmetric. And also we would like to add a FIFO unit in our encryption, so like that you can actually load multiple data faster, and when the unit is is done with data, it loads in a different FIFO, so you can actually go and grab it whenever you want.
When you say we would like to, I mean, I'd like to do all kinds of things too. But I'm just kind of putting boundaries on that. These are things you think you could do if you had the time. In other words, like, oh yeah, I want to do superscalar,
Yeah.
But you think you could do that based on what you've done. Like you said, the MMX was close. You just testing it, you didn't have enough time or whatever.
Yeah.
But
Also,
the pipelining, did you start? And
yes, I
then,
did.
That's what I mean. So
Yeah.
it's not like just saying, yeah, I want to do this.
No, and actually the pipeline we did start. We were halfway into it, but because of time, I had to go back. I couldn't make it on the time limit.
Yeah.
We were trying to shoot for the superscalar, but we were first doing the 1 clock on pipeline. And for the RSA, I know how it's done because of different mathematics class that we have. But we have to look into how can we code it into Verilog. And the FIFO units, they're just a register file, and it's just having a way to control it when you save it and when you get data from it. And so all those enhancements are possible, just with one more time.
Yeah.
At this time, I'd like to thank you. We would like to thank
Thank
you
you.
for listening. And we're open for any suggestions or questions and answers.
Questions?
For just because I don't know, but the ALUs, you had them all running at the same time, you just select which one you go into?
No, they'll run at the same time, so all of them get the same data. But at the end, you
Which
only select
results?
one output from it.
Oh, okay.
Yeah, we didn't want to add extra control signals for those ALUs. So they're on parallel, so they always run them.
Do all those ALUs have the same instructions as the baseline ALU?
Yes, but there is the 3 new ones, multiplication, division, they don't implement it the same way. We just, we do a multiplication and division, and we just only return depending if it's an 8-bit multiplication, we only return 8 bits. You don't get the upper 8 bits, like on the 64-bit implementation.
So does one output quicker than the other? Because it's a for loop, I'm assuming, right?
Yeah, but in case inside the control unit, you still implement the multiplication, but instead of going into multiplication part 2, that is in the 64-bit, the one that you actually grab the upper 64 bits of your result. On the 8, 16, and 32-bit ALUs, you just do one multiplication statement, and you just get one answer, and then you go back to fetch.
So you use the Verilog multiply operator, is that what you're saying?
Yes, correct.
Yeah.
We could have done the actual algorithm that we had at the beginning, but because of time,
Right.
and we just went straight to the multiplication and division. And we didn't want to go with a trailing word, the result in the upper 8 or 16, because it was going to add more complexity, and the time that we had wasn't allowing us.
Understand. I think we're out of time, but that was excellent. Very good.